What's up, my pre-calc people? In this video, we're going to tackle topic 3.12 on equivalent representations of trigonomic functions. Now, the primary focus of this topic is on the trigonomic identities, and there are a lot of them that you need to be able to use and understand. There are several different sets of trigonomic identities that you need to be able to know. There are the reciprocal identities, the quotient identities, the Pythagorean identities, the sum and difference formulas, and the double angle formulas. Now in this video, I'm going to quickly walk you through where these formulas come from and how they are derived. And then in follow-up videos, I'm going to talk about how we can actually use these identities. In this topic, the main thing we need to be able to do with the trigonomic identities is simplify trigonomic expressions or trigonomic functions, verify additional trigonomic identities, and use them to help us solve advanced trigonomic equations and inequalities. All right, so let's dive into exactly what those identities are and how they're derived, and then in future videos, you're going to learn exactly how to use them. So the first set of identities we want to talk about are the reciprocal identities and the quotient identities. These are the pretty easiest to understand. Now, where do these come from? Remember, we learned that sine of theta equals y over r when you are on a non-unit circle. And we know that the reciprocal is cosecant of theta, which is r over y. That means that sine and cosecant are reciprocals. Hence, sine of theta equals 1 over cosecant, or cosecant equals 1 over sine. And the same can be true for cosine, secant, tangent, and cotangent. Now, we also learned that tangent is the representation of the slope of the terminal side of the angle. And that also means that tangent is y over x, because that's slope, change of y over x. But since sine is y and cosine is x, then we also know that tangent is sine of theta over cosine of theta. Same for cotangent. Cosine of theta over sine of theta, the reciprocal. So these identities are used quite often when we're talking about simplifying, verifying, or solving equations. Now let's talk about possibly the most popular identities, and those are the Pythagorean identities. Now they all stem from this setup. We know that in a unit circle, the point P, that is where the terminal side intersects the circle, the vertical displacement is your sine of theta. That's the y-coordinate. And the horizontal displacement from that angle is cosine of theta, or the x-coordinate. Now if we look at this, we get a pretty easy theorem going to the Pythagorean theorem, and that is that x squared plus y squared equals 1 squared, that's the radius, which is of course just 1. 1 squared is 1. And that's a really powerful idea there. And from that, we can incorporate our trigonometry. We know that x is the cosine value of theta. Therefore, cosine of theta squared. And we also know that y is the sine value of theta, so we could replace that y with sine of theta squared equals 1. Now, typically we write this as mathematicians get a little bit lazy. We don't like writing those parentheses. So we move the square after the s of cosine. So we get cosine squared plus sine squared equals 1. And this is the main Pythagorean identity. And all the other Pythagorean identities stem from this. Now, first off, this identity right here can actually be manipulated in a couple different ways. Again, you are allowed to move things left to right. Identity is simply anything that's true for every value that you plug in. So no matter what you plug in for theta, this will be a true statement. So for example, a couple different manipulations of this. I can subtract the cosine squared to the other side, and I get sine squared of theta equals 1 minus cosine squared of theta. I could even continue that further and subtract the 1 to the other side and get sine squared of theta minus 1 equals negative cosine squared of theta. Again, lots of different manipulations, and I'll keep going. I could also subtract the sine squared over. So I get cosine squared of theta equals 1 minus sine squared of theta. Again, all I'm doing is taking the original Pythagorean identity, cosine squared plus sine squared equals 1, and manipulating it to make it look a little different, but not be different. Next, I want to show you how we could derive a couple more Pythagorean identities. If we take this main Pythagorean identity that we just talked about, and I divide every single value, divide the whole thing by cosine squared. Now, as long as I'm doing it to all three parts, I'm totally okay. Now, what happens here? Well, cosine squared divided by cosine squared is obviously 1. Sine squared divided by cosine squared is going to be tangent squared. Now, we already talked about the quotient identities, that sine divided by cosine is tangent. But if I have sine times sine divided by cosine times cosine, then I could do tangent times tangent, which can generate tangent squared. And then likewise, 1 over cosine is secant, so 1 over cosine squared would be secant squared. So I get another Pythagorean identity based on the original, that 1 plus tangent squared equals secant squared. And then once again, I can manipulate this. For example, I can subtract the 1 to the other side, and I get tangent squared of theta equals secant squared of theta minus 1. Just another representation. Now, another thing I can do is instead of dividing everything by cosine, I could divide everything by sine. All right, what would happen there? If I divide everything by sine squared of theta, divided by sine squared of theta, divided by sine squared of theta, let's see what happens. Well, cosine squared divided by sine squared is going to be cotangent squared of theta. Again, we know that cosine divided by sine is cotangent. Squared, you're going to get cotangent squared. Sine squared divided by sine squared is going to be 1, and 1 over sine is cosecant, so 1 over sine squared is going to be cosecant squared. So again, we get another Pythagorean identity built from the original cosine squared of theta plus sine squared of theta equals 1. So here are those main 3 Pythagorean identities. And don't forget that all of them can be manipulated a little bit to look different without being different. All right, let's talk about something else. Now, here's something very, very interesting we could do. Instead of having x and y, we could write y in terms of x. All right, let me explain this real quick. So we know that we have this triangle here, and we know that we have a radius of 1, that's the hypotenuse. We already know that that horizontal displacement is x, and again, we were calling the vertical displacement y. But what if we didn't want to use y? We wanted to replace y with something that is in terms of x. So we're going to put like a question mark right here. What could I put there that is same thing, but in terms of x? Well, I could use Pythagorean's theorem. I know that x squared plus question mark squared equals 1 squared, which is of course 1. I could subtract the x squared over, so I get question mark squared equals 1 minus x squared. Take a square root, and we get that this missing side right here is the square root of 1 minus x squared. So instead of saying y, we could write y in terms of x. And to do so, that value y, the vertical displacement, would be the square root of 1 minus x squared. Now, in this picture, we know a couple things. We know that cosine of theta equals x. Okay, I hope that's pretty obvious, which means that x equals, well, hold on, let me restart that. I apologize. I could do the inverse, and that means that theta equals cosine inverse of x. Okay, simple. I could also do that sine of theta equals, well, traditionally we say y, but remember, we wrote y in terms of x. So therefore, sine of theta equals the square root of 1 minus x squared. And then I could also say that theta equals sine inverse of the square root of 1 minus x squared. Now, this theta right here is the same theta as right there. It's the theta from our picture, which means that cosine inverse of x equals sine inverse of 1 minus, the square root of 1 minus x squared. This gives us what we call the inverse identity. It's pretty simple, and again, some kids get confused by it, but again, all we're doing is writing y in terms of x. And if we draw that triangle, very, very simple to do, we get that y in terms of x is the square root of 1 minus x squared. The next set of identities are known as the sum identity for sine and the sum identity for cosine. These, unfortunately, you just kind of have to memorize a little bit for the most part. But here's how it works. Sine of alpha plus beta, where alpha and beta are 2 different angles, equals sine of alpha cosine beta plus cosine alpha sine of beta. So we have alpha, beta, but we alternate sine and cosine. So we have sine, cosine first, sine alpha, cosine beta. Then we switch to cosine alpha, sine beta. A little bit confusing, takes some time to practice. All right, then we have cosine of alpha plus beta as well. Here it's a little bit different. It's cosine alpha, cosine beta, sine alpha, sine beta. So once again, it goes alpha, beta, but it's cosine, cosine together, and then sine, sine together. And the other thing we notice is it's addition, but the formula uses a minus sign. So a little bit different there. Now, from the sum identities, we could derive the difference identities. So imagine if we had sine of alpha plus negative beta. Now that would be equal to sine of alpha minus beta. But if we write it as addition, we could utilize our formula. So here's how it would work. It would be sine of alpha times cosine of negative beta plus cosine of alpha times sine of negative beta. And we can put some parentheses around that alpha there. Now, from here, we know that cosine of a negative angle is the same thing as cosine of the positive angle. So we could write sine alpha cosine beta. Again, I'll say that one more time. Cosine of a negative angle is equal to cosine of a positive angle. Plus, now back here, we know that sine of a negative angle is equal to negative sine of that angle. So basically, this negative sign could come out in front, and it's going to turn this plus sign into a minus sign. So we put a minus sign here, and we get cosine of alpha times sine of beta. Okay, so that's how we could derive difference formulas from the sum formulas. Now, I'm not going to bore you by doing that again with cosine, but here they are. Here are the difference identities. So again, sine of alpha minus beta is sine alpha cosine beta minus cosine alpha sine beta. Pretty straightforward, not too difficult. Just going to spend a little bit of time studying and practicing it. Then for cosine of alpha minus beta, we have cosine alpha cosine beta plus sine alpha sine beta. So notice that the difference formula uses a plus sign for cosine, and the sum formula uses a minus sign that we saw earlier. Now, the other thing we could do with the sum formulas for sine and cosine is we could derive what we call the double angle formulas. Now, imagine we had sine of 2 alpha. Okay, sine of 2 alpha. Again, a double angle. Not addition, but a double angle. 2 alpha, a double angle, right? Okay, so what we could do here is we could write this as a sum. That would be sine of alpha plus alpha, because another way of saying 2 alpha is alpha plus alpha. Now what I could do is I could utilize the sine or the sum identity for sine. Okay, so here I go. I get sine of the first angle times cosine of the second angle, but the second angle is also alpha, plus cosine of the second angle, alpha, times sine of the first angle, alpha. Okay, so let's see here. We have sine alpha, cosine alpha, and then we have cosine alpha, sine alpha. Now, the order that you multiply does not matter. That is something that holds true in trigonometry as well. So we have sine of alpha, cosine of alpha, and then back here we can switch this around. Cosine times sine is the same as sine alpha times cosine alpha, and that allows us to say, well, wait a minute, if we have a sine cosine and another sine cosine, those are like terms, so we can combine them together to get 2 sine alpha cosine alpha. Now, we could do something very similar with the sum identity for cosine as well to figure out what cosine of 2 alpha is. But I'm not going to bore you with that right now in this video. You could try that on your own. Hopefully you tried that in class. But here are those double angle identities. As we just pointed out, sine of 2 theta equals 2 sine theta cosine theta. Now, notice I'm calling it theta here when I just got done calling it alpha. It doesn't really matter what you call the angle. And then the double angle for cosine, we actually have 3 options based on how we can incorporate the different ideas. And I can show that in a later video if you want. But for cosine of a double angle, you got 3 different options. 2 cosine squared minus 1, 1 minus 2 sine squared, and cosine squared minus sine squared. But you know what? The more I think about it, the more I kind of want to show you where these formulas come from. All right, so I'm going to do cosine of theta plus theta. Again, I'm taking the double angle and I'm writing it as a sum. All right, now I'm going to use the sine, excuse me, I keep saying sine, the cosine of our addition formula. All right, so that's going to look like this. Cosine of the first angle, cosine of the second angle, minus, remember it's a plus, use a minus sign for cosine. It's sine of the first angle, sine of the second angle. So pretty quickly you realize where we get that bottom formula from. Cosine theta times cosine theta is cosine squared theta, minus sine theta times sine theta is sine squared theta. Okay, but now check this out. I can incorporate some of those Pythagorean identities. I could literally replace cosine squared with 1 minus sine squared. Let me explain that real quick. We learned the Pythagorean identities earlier in this video that cosine squared plus sine squared of theta equals 1. So if I subtract the sine squared over, I get that cosine squared of theta equals 1 minus sine squared of theta. So I'm going to replace this cosine squared right here with 1 minus sine squared of theta. The other minus sine squared of theta is still there from the back, and I get 1 minus 2 sine squared of theta. That's how I could derive that second formula. Now, what about the first formula? Well, I'm just going to do something very, very similar. Instead of subtracting the sine squared over, I'm going to subtract the cosine squared over, and I know that sine squared of theta equals 1 minus cosine squared of theta. It's just a manipulation of the Pythagorean identity. So this time, I'm going to replace sine squared of theta with 1 minus cosine squared. So here I go. I have the cosine squared of theta in the front. And then I'm going to replace the sine squared with 1 minus cosine squared. Notice I needed parentheses because I'm going to have to distribute that minus. I'm only replacing the sine squared, not the negative. So now I'm going to distribute that negative, and I get cosine squared of theta minus 1 plus cosine squared of theta. And that's how we get this top identity, that 2 cosine squared of theta minus 1 is another representation of cosine of 2 theta. So long story short, there's lots of identities that you need to know and understand, but you also have to understand how those identities can be manipulated into other identities. All right, now the last thing we're going to talk about is what we're actually going to talk about in the next couple videos, and that is that what do we do with these identities? Well, there's a couple main things that we do. We can simplify trigonometric expressions or trigonometric functions. We could use the identities to help verify more identities, and we could help use them to help solve more advanced trigonometric equations. So stay tuned for future videos that are going to walk you through how these identities are actually used in those situations.